happy Thursday, or whatever day this ends up being. I think this is going to end up being Thursday's lesson. But if that's not the case, then happy day, whatever day it is. So today we're going to go through section 3.2 on complex numbers. And complex numbers include what we call an imaginary number, and that's what I kept mentioning the last couple days. And the imaginary unit, so when we refer to a unit, like a single unit, so a single imaginary unit, so an imaginary number, is defined as I squared equals -1. But the actual imaginary unit is the number, the number I. So I is the square root of -1. So that is I equals square root -1. Because if we know I squared, so the idea is I squared is equal to -1. So if you take the square root of that, then we get I equals the square root of -1. And the principal square root means just positive square root of -1. So kind of weird. And there's different forms that imaginary numbers can be in to still be considered what we call a pure imaginary number. So there's imaginary numbers, and then we're going to look at complex numbers. It's a little bit more broad. So an imaginary number can be like 6i or negative something I, or you can have I times the square root of something. And they are basically square roots of negative real numbers. And if you have a real number in front of the square root, or if you're able to take a negative number or take a number out of the square root, it is written in this form. So for example, let's say we had the square root of -25. That's the same thing as 25 times, and then the square root of -1. And we can define the square root of -1 as I, so that's just 5i. So whatever variable you have in here, if it's a quantity squared, you can take out that quantity, and to deal with the negative inside the square root, you take out an I. So again, it's super weird at first, but it's not bad once you get the hang of it. So this first example, it says simplify the square root of -27. So I'm going to start by writing that's the square root of 27 times the square root of -1. So 27, the numbers that go into 27 are 9 and 3, so I can take out a 3. That's 3, and then there's a 3 left in the square root. And then the square root of -1, again, we can replace that with the letter I. So in terms of the order you write it in, first is the coefficient, then you put the letter I, and then the radical. So this is 3i rad 3. So it's basically just doing the square root of 27 and then putting an I out in front because it was negative inside the square root. For part B, it's the square root of -216. So that's 6 and 36. But I'm going to write this as the square root of 216 times the square root of -1. And then again, we can take out an I. And so we have I times the square root of 216. Since it's divisible by 36 and 6, we can take out a 6 from 36. So that's 6i, and then we have a 6 left inside the radical. So go ahead and pause the video, do the first try this problem. And once you're back from doing the try this problem, we're going to go over some properties of imaginary numbers. And basically the commutative and associative properties, so that's looking at the ordering and the grouping of imaginary numbers, is the same as what we use for real numbers. And we're going to look at a few problems like this in the practice problems in class tomorrow. But so we're not going to go too far into it now, but we are going to look at some tomorrow. So to keep it simple, I to the first power is just I. If you have I squared, so that's I times I, that's the square root of -1 times the square root of -1, you get -1. If you take I squared, so -1, and multiply by I, you get -I. And then if you do I to the fourth, that's -1 squared, because I squared is negative 1, and then you get positive 1, and then this just keeps repeating. So again, I to the first is I squared is negative 1, I cubed is negative I to the fourth is 1, and then it repeats. So I to the fifth is the same thing, it's I to the sixth. So I to the sixth would be negative 1, I to the seventh is negative I to the eighth is positive 1, okay? So super weird, but basically when you keep multiplying by I, you keep going back around. So every time you go up by 4, it's getting you back to one of these original values. So again, we'll go into that tomorrow, don't worry about that. But just want to kind of intro it a little bit. So for example 2, we need to simplify. So we have negative 5i times positive 3i. So this is negative 15, and then we have I squared. Well, I squared is equal to negative 1. So this is negative 15 times negative 1, which is just positive 15. Weird how we can get from negative 5i times 3i to positive 15. And then part B, it's the square root of negative 6 times the square root of negative 15. And you cannot just do the square root of negative 16 times the square root of negative 15 and say, oh, well, those make a positive. So you cannot bring two radicals, what's inside two radicals, together if it's a negative in there. What I mean by that, if it was positive 6, positive 15, you could just go square root of 90. But that property does not hold for imaginary numbers. So here we have the square root of negative 6, that's square root of 6 times square root of negative 1, or I'm just going to start writing I to represent that. I'm not going to keep writing square root of negative 1 each time. And then this is the square root of 15 times I. So we have the square root of 6 times I, don't know the square root of 6, we're just going to keep it like that. And then times I square root of 15. Now that we've taken the I out, we can now bring the 6 and the 15 together and say that's the square root of 90, which is 9 times 10. So we can take out a 3, which would be 3i rad 10. Now if you, come on, there it is. So, oh, wow, actually, I just caught myself. All right, if you found my mistake, good job. I'm glad I found it before this video is over. I went from this middle step, so I times I, and I forgot one of the i's. So that's I squared times 3 rad 10. But I squared, we know I squared. I squared is negative 1. So that's negative 1 times 3 rad 10, which is negative 3 rad 10. So if you caught that as we were working through it, then good job. If not, make sure you correct that. So I'd lost an I, not, well, geez, that would be bad if I lost an I. I lost an I in math terms. So yeah, that's better than losing an actual one. All right, talking to myself. So the next one, try this, go ahead and pause that, and then when you're ready to continue, you can keep it going. So example 3, it says equations with imaginary solutions. So yes, we're going to be getting some imaginary solutions in here. And this first one says x squared plus 64 equals 0. So there's two different methods we're going to look at. The first one is the square root property. So I'm going to take x squared plus 64 and get x squared by itself. So that would be x squared equals negative 64. So to get rid of x squared, take the square root. We get x equals plus or minus square root of negative 64. That's 8i. So where did that come from? Well, this is just square root of 64 times square root of negative 1. Square root of negative 1 is I. So that's one method you can use. The other one is factoring, which is kind of weird, but I do want to go into it to make sure that you see the connection for how you can end up solving any quadratic. So x squared plus 64 equals 0. In order to factor this, what we would normally do in chapter 1 is say, is this a difference of squares? So that's a perfect square and that's a perfect square. But this is not the difference of squares because it's being added together. But we can turn it into the difference of squares if we go x squared minus negative 64. So, and keep in mind this here, this is an imaginary number. So that's x squared minus, and then this is going to be negative 8 squared. So, and this can get a little funky. So another way you can write this is to say square root of negative 64 squared. And then this is x minus, and then the square root of that term. So that's going to be 8i, and then x plus 8i. So then we get x equals 8i, and x equals negative 8i. So if that way didn't make as much sense, that's okay. You can always do it with the square root property. Just trying to show you that it's the same thing as difference of squares, except with a negative square, and that works out. You can have a negative square because of imaginary numbers. All right, let's keep it going. I'm hoping to do all this in one video. I don't know how long it's been, hopefully not too long. So if you think about 2 plus 3i, so normally we would say that this is two terms, but we're actually going to call this a number. So this is referred to as a complex number. And it's a complex number, partially because it's complex, but because there's two parts to it. So there's the real part, which is the number 2, and then there's the imaginary part. So 3i. So it's not just the I that's imaginary, it's 3 times I, so it's 3 of I. So that's the imaginary quantity, the imaginary number. And the terms are not like terms and can't be combined, so this is referred to as a complex number. And the general form that it's written in is a plus b times I. So a is a real number, b is also a real number, but this quantity, so b times I, this whole quantity is considered imaginary. So again, complex number written in the form a plus b times I. A and b are real, but this quantity b times I is imaginary. So this would be the real part. This here is imaginary. And then this is just showing you that 1 minus 3i, that's the same thing as 1 plus, and then this is a real number, but in front of I. So if you think about any real number in general, like let's say the number 7 plus, if we had 0 times I, so technically every number, every real number is still a complex number, but the b value is 0, so it's just not there. So you're just left with the number. All right. So example 4, it says find the values of x and y that make this quantity true. And this is, again, a little weird to start, but once you see it, it's super simple. These next two problems are super easy. So we've got this quantity plus y minus 3 times I, and that's equal to 7 plus 6i. So again, up here we said that those terms are not like terms. So this quantity here is not a like term with that quantity because one of them is being multiplied by I and the other is not. It's the same idea as if we had like 3x minus 5 plus y minus 3 times and then a variable. Let's just say z, since I already used x and y, equals 7 plus 6 times z. You cannot combine these terms with those because these are multiplied by z. So they're not like terms. Okay, so we want to set the real parts equal. So again, the 3x minus 5 is not multiplied by I, so that part is real. And on the right side, the 7 is not multiplied by I, so that part is also real. So we set those equal. You get 3x equals 12, so x has to be equal to 4. and then the imaginary parts are going to be equal to each other. So I set y minus 3, the quantity in front of I, equal to 6i, which means y minus 3 is going to be equal to 6. So y is 9, and that's it. It just says to find the values of x and y. So x equals 4 and x equals 9. And if you're like, what does that actually mean? I'm going to go ahead and plug them in so you can see it. So if we plug in 4, 3 times 4 minus 5 plus y is 9 minus 3 times I equals 7 plus 6 times I. That's 12 minus 5 is 7 plus 9 minus 3 is 6. So 7 plus 6i equals 7 plus 6i. So again, you set those real quantities equal, and then the imaginary quantities equal. And because we're just looking at the coefficient in front of I, you just set those equal and you can get the variable. So this next one, it says find the values of x and y that make this true. So look at your real portion. So this part is real. This part is real because it's not attached to I. And then the imaginary parts, that's 3 plus 2y times I. And then y minus 6 times I. So we're going to set those equal. 5x plus 1 equals, on the right side, 2x minus 2. And then for the imaginary terms, we have 3 plus 2y equals y minus 6. So I'm going to subtract 2x from both sides, subtract 1 from both sides. We get x equals negative 1. And then over here, subtract y from both sides, subtract 3 from both sides. So y is negative 9. And again, you could plug those in to make sure that they work. If that helps you out to check it, go for it, but you don't have to. All right, 2 more types of problems. So we're going to add and subtract complex numbers. This one's also pretty straightforward. So in order to add or subtract, again, they have to be like terms. So you want to add the real parts together. And then we're going to add, I am not being consistent with color. So these are the imaginary parts. And then we're going to add the real parts together. So 5 plus 2, that's 7. And then negative 7i plus 4i is negative 3i. And that's it. If it helps you to write them out, you can go 5 plus 2, and then negative 7i plus 4i, and then combine them together. And this is a try this. Make sure that you distribute the negative to both of those terms, and then combine them together. And you always want to write the real part first, and then the imaginary part, because it takes the form of a plus b times I. So real part first, then imaginary. Again, pause the video, get that done. And then these last 2 problems are dividing by complex numbers. And when you have 2 complex numbers, so a plus bi and a minus bi, these are referred to as complex conjugates. And the product is always going to be a real number. And so we can use that to simplify. You cannot have an imaginary number in the denominator. It's considered unsimplified, so it needs to be simplified. However, we can always get rid of it from the denominator. So the way to do that is by using the conjugate. And I'm just going to do a quick recap on what you've already learned about this. So what we have already gone through is like if you have, let's just say 10 over and then 2 plus the square root of 3. So with radicals, you cannot have a radical in the denominator. That's not considered simplified. So to get rid of it, we would go 2 minus rad 3 to minus rad 3. And this is referred to as the conjugate. And to come up with the conjugate, it's just the opposite sign for the second term. So 2 plus rad 3, instead we multiply by 2 minus rad 3. And I'm going to show that down here. So 2 plus rad 3 times 2 minus rad 3. In the process, we get, you can FOIL 4 and then minus 2 rad 3 plus 2 rad 3 minus, and then rad 3 times rad 3 is just 3. So those cancel out. So again, if you multiply by the conjugate, it's always going to cancel out the middle terms, which gets rid of the radicals. And this is the same concept for imaginary numbers. So for part A, we're looking at this, and we're going to treat just like we did if this was a radical, we want to get rid of that. So we want to get rid of the I. So to get rid of it, we're going to multiply by the conjugate, which is 3 minus 6i over 3 minus 6i. So that's 2i times 3 is 6i. Again, it works just like a variable. And then minus 12 times, we have I squared, which we're going to be able to simplify. And this is all over. And then in the future, you can just go straight to doing the first terms and the last terms. Or you can write it all out if that helps you. I'm going to show what all of it multiplied out would get. So 3 times 3, that's 9. Outer terms would be negative 18i. Inner terms makes positive 18i. And then the last terms, that's negative 36i squared. And I like to write out I squared, not just go straight to -1, because again, you can mix up those signs. So as I was saying, those inner terms cancel each other out. And again, you can skip that step. You could go straight to 9 minus 36i squared. You don't have to write them. That's just if that helps you to see it. And so from here, we have 6i minus 12 times I squared is -1. So that's going to be positive 12 all over. And then we have 9 minus 36 times -1. So that's 6i plus 12 over 9 negative 36 times -1 is positive 36. So we get 6i plus 12 over 45. So now there's no imaginary number in the denominator. So it's acceptable. However, this is not fully simplified. So all 3 of the terms are divisible by some number. What number is that? It's 3. So we can divide by 3. Not sure what I'm trying to do there. Divide by 3, divide by 3. So that's 2i plus 4 over 15. And this is our simplified version of what we started with, 2i over 3 plus 6i. So you've got one more try this problem, and this one's a little bit different, so I'm going to help you get it started. Again, if you had in the denominator some number, so whatever it is, a plus b times I, you would multiply by a minus b times I, so the opposite sign. But since this is just over 5i, so if it's not complex, this is just an imaginary number, it doesn't have a real part, you can actually just multiply by I over I. That will get rid of I from the denominator. So go ahead and finish that out, and then you are good. Thanks for listening. Thanks for watching the screen, not watching me. But anyway, have a great rest of your day, and I'll see you next time. Well, I won't see you.